Objective of choosing the Laplace transform in biomedical data analysis and modeling. Firstly, the Laplace transform chosen in biomedical data analysis and modeling primarily because it provides a powerful mathematical tool to analyze system described by linear differential equation, which are common in biomedical systems. Here are some specific objective and advantages. Firstly, solving differential equations. Many psychological processes can be described using differential equations such as those involving growth, decay, circulation, and diffusion of substances within biological system. The Laplace transform allows this differential equation to be transformed into algebraical equation, making them easier to solve analytically. Second, stability analysis. The Laplace transform is crucial for stability analysis of biomedical system. By transforming differential equation into the Laplace domain, stability criteria can be analyzed more easily, helping to understand how particularly of changes in parameters affect the overall stability of biomedical system. Overall, the choice of a Laplace transform in biomedical data analysis and modeling is driven by its ability to simplify the analysis of complex dynamic system, facilitate solution of differential equation, provide insight into system behavior in the frequency domain, and support the design and analysis of control system relevant to biomedical application. So, method used for calculation. My question is, my question sounds as a biologist is studying the growth of a bacteria population NT over time in a controlled environment. The growth follows exponential kinematics with a growth rate R equals to 0.05 per minute. Initially, there are n times 0 equals to 100 bacteria. So firstly, we involve differential equation. The growth of bacterial population follows exponential growth kinetics, which is described by the differential equation, found as dnt over dt equal to r and t, where r is the growth rate constant. Given r equals to 0.05 per minute, the differential equation will become dnt over dt equals to 0.05 nt. So the second method involved in the calculation is the Laplace transform. So to solve this differential equation using Laplace transform, we apply the transform L to both sides. L dnt over dt is equals to S and S minus n times with O. Since NO equals to 100, we have S and X minus 100 is equal to 0.05 and S. Rearranging to solve this, S and S minus with 0.05 and S equals to 100. So if we simplify this, in the end of this, we will get NS is equals to 100 over S minus 0.05. Therefore, the Laplace transform Ns of the bacterial population Nt is equals to 100 over X minus with 0.05. So, as a conclusion, the Laplace transform approach provides a quantitative framework to analyze and predict bacterial population dynamics under exponential growth kinetics. It enables researchers to calculate the population size at any time t, assess the impact of differential growth rates on a population growth, and compare experimental observation with theoretical prediction. In conclusion, the application of Laplace transform in studying the growth of bacterial population facilitates a rigorous quantitative analysis of population dynamics, offering insights into biological growth process in controlled environments and supporting experimental design and data interpretation in microbiological research. Thank you.
The objective of second-order linear differential equation with constant coefficient in bioprocess control. So the first objective is modeling dynamic system. Second-order linear differential equations are used to model the dynamic behavior of bioprocess system, including microbial growth, enzyme reaction, and substrate consumption. These models help in understanding how the system responds over time to different inputs or disturbance. So the second objective is stability analysis. These equations allow for the analysis of the stability of bioprocess system by examining the solutions of the differential equation. One can determine if the system will return to a steady state after a disturbance or if it will exhibit oscillatory or unstable behavior. Method of solving. So my question is, consider a bioreactor where the biomass concentration Xt needs to be controlled. The system's response to change in the nutrient feed rate can be modeled by a second order linear differential equation with constant coefficient. So the equation given is d2x over dt square plus 4 dx dt plus cx equals to 6 UT, where the XT is the biomass concentration at time and UT is the input nutrient feed rate. Assume the initial condition is x0 equals to 0 and d2x over dt square equals to 0. Determine the biomass concentration as a function of time if a step input UT equals to 1 for t more than 0 is applied. So when it comes to the solution, first since the question already gives the step input where ut equals to 1, we directly substitute the ut value in the given equation which is d2x over dt square plus 4 dx dt plus cx equals to 6 ut. So hence the equation will become d2x over dt square plus 4 dx dt plus cx equals 6. Second, we will apply Laplace transform. Taking the Laplace transform from both sides, we will get s square xs minus sx0 minus ds dt 0 plus 4 sxs minus x0 plus 3xs equals to 6 over s. Given the initial condition x0 equals to 0 and dx dt equals to 0, this simplifies to s square xs plus 4s xs plus 3xs equals to 6 over s. The third step is solve for excess, where we have to factor out all the excess, which it will become excess in bracket s square plus 4s plus 3 equals to 6 over s. Then we will perform partial fractional decomposition. So we have to decompose the excess where the equation will become 6 over s bracket s plus 1 s plus 3. By using the partial fraction, we have to find out the value of a, b and c. Hence, the value of A we will get 2 and the value of B we will get negative 3 and C we will get negative 1. Hence, the excess solution will become 2 over S plus 3 over X S 3 over S plus 1 minus 1 over S plus 3. The final step is take the inverse Laplace transform. So we have to refer to the table to take the inverse Laplace transform where the final solution will be xt equals to 2 plus 3 exponential negative t minus exponential power of negative 3t. So the conclusion is second order linear differential equation with constant coefficient are invaluable tools in the field of bioprocess control. They provide a robust mathematical framework for modeling and understanding the dynamic behavior of bioreactors, which are essential components in various biotechnological and pharmaceutical industry. Thank you.
Okay, the objective of second order linear differential equation with constant coefficient in gene expression dynamic. First objective is modeling temporal dynamic of gene expression. Second order differential equation can model oscillatory behavior in gene expression which are common in biological systems such as circadian rhythms. Second objective is analyzing gene regulatory networks. Second order differential equation can describe the interaction between multiple genes and their products, capturing the complexity of gene regulatory network. Final objective is Quantifying gene expression noise. Although second-order differential equations are deterministic, they can be used as a basis for understanding the effects of noise in gene expression when combined with stochastic models, analyzing how intrinsic and extrinsic noise affects gene expression level. Okay, my question is find the general solution of the equation. The question is y prime prime plus y 4y prime plus 3y equals to 2x squared minus 1. Okay, the solution is first we substitute m variable in the original equation and equals to 0. Okay, the equation be like m squared plus 4m plus 3 equals to 0. When we solve the equation, we get two roots, which is -1 and -3. Okay, b square more than 4a square. I use the equation to find the general solution, which is y equals to ae m1x plus be m2x because the b value more than the 4ac. So we, according to the table, we choose the first equation. So the YC equation be like AE negative x plus BE negative 3x. So now we identify the YP equation. The equation is XR bracket AX squared plus BX plus C. So uh, we substitute R with maybe 0, 1, 2, 3, and etc. So the R is like try and error. So I try with 0. If we substitute the R value, we get one equation. The equation is not same to the YC equation. If same, we try we move to another value like we substitute with 1 or 2 to get not same with the YC equation. So in this situation, uh, I substitute with 0 and the YP equation is ax squared plus bx plus c, which are not same with YC equation. So we proceed with other step. So we differentiate the y first differentiate the YP equation. So the equation be like 2ax plus b. The second time differentiate, we get to a. So the equations we must substitute with into the y prime prime plus 4y prime plus 3y equals to 2x squared negative 1. If we substitute, we get 3ax squared plus 8a plus 3bx plus 2a plus 4b plus 3c equals to 2x squared minus 1. If we compare to the 2x squared minus 1 equation, we get the a, b, c value, which is a equals to 2, b equals to negative 16 over 3, c equals to 13 over 9. Okay, YP equation is to the value we substitute to the YP equation. So the YP equation be like 2x squared minus 16 over 3x plus 13 over 9. Y equals to YC plus YP. So the Y equation AEX AE negative x plus BE negative 3x plus 2x squared minus 16 over 3x plus 30 over 9. This is the solutions of y prime prime plus 4y prime plus 3y equals to 2x squared minus 1. Thank you. In conclusion, second-order linear differential equations with constant coefficients are useful tools in biotechnology, especially for understanding the dynamic regulation of gene expression. They assist researchers and engineers model analysis and forecast the behavior of complex biological systems, contributing to advances in synthetic biology, drug discovery, and system biology.
Objective of the applications are further differential equations in the batch culture growth in a bioreactor. So the first one is modeling growth rates. So the primary goal is to represent the rates of change of the microbial population in a batch culture. Their growth rates can often be described by first order differential equations. So the second one is predicting population dynamics. So this equations helps in predicting how the population evolve over time, enabling researchers to understand different phases of growth such as a lag phase, exponential phase, stationary phase, and death phase. So the last one is optimizing culture conditions. By understanding the growth dynamic, it becomes possible to optimize the culture the conditions. So for example, it's nutrient concentrations, temperature. This is to minimize the growth rate or biomass productions. For the method of the solving, so here is the example of the questions. So in a batch culture experiment, the initial populations of bacterial culture is 1 multiplied by 10 power 6 cells over a milliliter. So the specific growth rate k during the exponential phase is determined to be 0.4 hours minus 1. So the question is to calculate the population size after 5 hours of growth. Second one is to determine the doubling time of the bacterial culture. So the third question is if the culture enters the stationary phase after 8 hours, so what is the population size at the end of the exponential phase? So for the method of solving, the first question is to calculate the population size after the 5 hours of growth. So the NT is population of size at time. So N0 is initial population size, and lastly E is base of natural logarithm. So we can get all the data from the paragraph. So the specific growth rate K can be determined experimentally by plotting the natural logarithm of the population size ln n versus time t, and calculating the slope of the resulting the straight of line. So for the next questions is to determine the doubling time of the bacterial culture. So here is the equations. So the equation states that K is specific growth rates. So this parameter quantities the rate of growth during the exponential phase and can be experimentally determined from the slope of ln n over vs versus t. So for the dt, it's mean a doubling time. So the times it takes for the populations to doubling in size during the exponential phase, it is related to specific growth by these equations. So the batch culture grows quantitatively describe how the microorganisms grow over time in the closed systems. So we can get all the data from the paragraph and just substitute it to the value of the K. So for the last questions is to determine the population size at the end of the exponential phase. So this question will just change the time with 8 hours. So over here we can see that we use the first order differential equations to solve this. So and the last one, we will get the answer for 24.532 divided by 1 divided by 10 over 6 cells per milliliters. So for the conclusions, in batch culture growth, the exponential log phase of the microbial growth can be modeled using the first order differential equations, which is the n over t equals to kn, where the growth rate is proportional to the current population size. The solution to the equations is nt0 equals to n0 ekt. It allows us to predict the population size at any given time. So this model was applied in the example calculations to determine the population size after 5 and 8 hours. So it's demonstrating how the exponential growth can be quantitatively analyzed using the first order differential equations.